One day I was playing Minecraft and I was trying to light up a hallway that was 12 blocks long with lanterns. I wanted to space the lanterns equally apart, but it seemed like no matter how I did it, it just did not work. If I had a hallway only 8 blocks long, it would have been fairly easy. I could just place the lanterns 2 blocks apart, and then I have 2 empty spaces between the lanterns and on either side of them. But with 12 blocks, nothing I did seemed to work. I was getting frustrated, and so the only thing I could do was to turn to math. In this video, I will make the following two assumptions. Number one, you are interested in building in Minecraft, and number two, you understand modular arithmetic. Suppose we have some integer length. We want to partition this length into two kinds of shapes, into posts and edges. We start off with a post and then alternate between an edge and a post until we end up with another post. We say that all of the posts are the same length and all of the edges are the same length, but we have to have each of them be at least one. For every pattern like this, there will always be one more post than there are edges. If an edge has a length of 1, this is like a lantern example, but if the post has a length of 1, then this is like partitioning a length into equally sized rooms. One thing that we can find right away is the entire length when we know how long each post and edge is. Let's say that the length of each post will be A, and that the length of each edge will be B, and that we'll have n edges. That means we'll also have n plus 1 posts. We can combine this into an equation for the entire length, where the length is equal to the length of the post times n plus 1, how many there are, plus the length of the edge, b, times n, how many edges there are. When I first started this problem, I looked into how many ways there are to partition some length into posts and edges, where posts and edges can't have length 0. For 3, there's only one way. You have to start off with a post, and then you have to have an edge, and then you have to end with a post. For 4, it's the same story. This is the only pattern that you can make. For 5, it's a little more interesting. You have these 3 different patterns. One where you have a post of length 2, and the edge is length 1. The next one where the post length is 1, and the edge length is 3. And finally the last one where every length is 1. For 6, there's only 2 ways. This would be a great time to pause the video and explore this problem a little bit by yourself. Try to look at larger lengths of edges. How many ways can you find to partition them into patterns? It was at this point that I wrote a calculator program to count up how many patterns there are for a given length, and I put the first few terms into this table. When I looked for the full sequence I'd found so far and searched it in the online encyclopedia of integer sequences, it seemed to be equivalent to this sequence, where the nth term is equal to n minus the number of divisors of n. It was at this point that the problem hooked me. There had to be some simple explanation that ties these patterns to the number of divisors of that length. But what? If the number of patterns for a given length L is equal to L minus the number of factors of L, there should be a way to match up patterns with integers that don't divide into them. So for 5, we have 3 numbers less than 5 that don't divide evenly into 5, 2, 3, and 4. It seems tempting to say that you can match these up by saying that the number describes how many white squares you have in each pattern, but this pattern breaks with the number of patterns for 6 and 7, where you don't have any patterns with exactly 5 squares for 6 or 7, and 7 has 2 patterns with exactly 4 white squares. This is where I spent a lot of head scratching looking for some leap in intuition to correlate these two numbers. I spent several hours trying to figure out some way to match them up, and I eventually did find a way, but we're going to look at a more direct route, where we can use the equation to exactly find how many patterns there are for a given length. Let's begin with that first equation we found for the entire length of the pattern. We can rearrange this into the following form, where the length of our pattern is just going to be the number of edges times the sum of the length of the post and the length of the edge, plus the length of one more post. If we take this equation, modulus the sum of a and b, this tells us that if we take our entire length of the pattern, modulus A and B, this will give us exactly the length of the post. This means that if we start off with this sum, there's only one option for what the length of the post has to be. That's a little hard to understand abstractly, so let's look at a specific example. So we start off with this modular expression, where the length modulus a plus b is equal to a. So let's say we have a length equal to 7, and we choose our sum of the post and the edge to be equal to 3. When we put together pairs of posts and edges, that leaves us with one post at the end, and this has to be the length of what the post is. And once we fill everything else in, everything else has to be an edge. That gives us this pattern based on the sum of the length of the post and the edge. We could do this with any length and choose some arbitrary sum, and it will always give us only one pattern for it. We can look back at those earlier patterns and see that the sum of the length of the post is going to be exactly equal to whichever number you wanted to pair them up with, and each sum will be unique for all of those patterns for that given length. We can look at larger examples where we've sorted all of the sums from top to bottom, least to greatest, and so here are a few smaller ones that I made using my calculator, and I think they look really cool. I call them like antlered pyramids or pyramids with antlers. But before we look at a few more of these, we haven't covered one thing. What happens if our sum is a divisor to our length, or our length modulus that sum is equal to 0? In that case, literally every block will have to be an edge, and so the post would have length 0, since that modulus is equal to 0. But we've already said that we don't want this, because we want the length to be greater than 0 for both the post and the edge. The pyramid for all of the patterns for length of 12 is instructive into why I couldn't place the lanterns nicely. If we look at all possible patterns, there's no way to have an edge of length 1. You might be thinking that we're missing a few rows, and we kind of are. It's just that we're missing all of the rows that are divisors of 12. And so we could include them, but you would just have a whole bunch of horizontal black lines of all edges. And since they don't give much information, I tend to not draw them. And that's why I'm pretty much only showing prime numbers for all the pyramids. So as we look at the pyramids, one thing you might wonder is like, what shape do they approach? And as we get into larger and larger prime numbers, you can kind of think of what it looks like. This is the final shape. It's not quite a fractal, since there are a bunch of places that you can zoom into that will have only finite complexity, but I think it's really cool nonetheless, and it's really fun to try to draw if you're bored in class at some point. So let's get back to Minecraft. How can you use this to make building easier? If you know that you will ever be subdividing some length into alternating posts and edges, you can try making that full length a prime number, since that won't have any divisors and you'll have as many patterns as possible to work with. Let's do a specific example. Suppose you have a given length of 38 and you want a post of length 2. First, you subtract the length of the post from that 38, so 38 minus 2 is 36, and you find all of the possible divisors. From here, you subtract that post length again, and so the possible edge lengths will be these here. We can't really have -1 or 0, so we'll just ignore those and look at what patterns all the others make. Then, depending on what size room or whatever else you're building, you can choose one of these patterns and hope that one of them will fit. You can use this same process if you have a specific edge length you want to match. In that case, though, you'll just add that edge length to your total number of the length. You'll find the divisors, and then subtract the edge length and find all possible post lengths from that. I've wanted to make this video for the Summer of Math exposition for a couple of years now, but I always procrastinate to the point of rewriting the script again and again when the deadline passes. I recently saw a video from the channel JMMIP where they worked through this problem but in a different way and came up with a really cool spreadsheet to find the best lengths to build walls out of. If you have any other questions or insights, please leave them in the comments. Thanks for watching.